Okay, problem 3 is about second order circuits. And for this problem, we're given the circuit shown below, 2 capacitors, a resistor, and inductor. So we have 3 energy storage devices, and we're asked to find both I sub L, the current through the inductor, and I sub 2 for time greater than 0. So the first question is, how are we going to approach this problem? There's 3 energy storage devices, so at first you'd expect it to be a third order circuit. But when you look at this a little bit more closely, you realize that these 2 devices over here, these 2 capacitors, they are in parallel. And because they're in parallel, you can simplify them. Now, if you simplify them, you will destroy the internal currents. But what's being asked are external currents to those 2 things. So you can absolutely simplify everything within the green box. Once you do that, you're left with just 2 energy storage devices, a single capacitor, a single inductor. You are switching it between 2 different DC values. From over here, for time less than 0, it looks like 2 amps. For time greater than 0, it looks like 4 amps. So therefore, you can use the second order switched DC approach. Now, I'm not going to go over all the details and all the variant types of a second order approach. I assume you've got the notes. If you don't, they're available for download on my website at www.jimsquire.com in the section on second order circuits under student notes. So we'll move through the various steps fairly fast. And the very first step, before we do anything else, is to simplify these capacitors. So capacitors in series work like resistors in parallel. Capacitors in parallel, though, just add. So we can add 1 over 400 and 3 over 400 to get 4 over 400, which is the same thing as 1/100th farad. And now that we've done this, we can begin working on the step-by-step approach that I outlined in my student notes. So the first step is to redraw for time less than 0 and to find our VC naught and our I sub L naught, no matter what we're asked to find. The VC naught for time less than 0 has to be by the voltage continuity of the capacitor, the same as the voltage at 0 plus. Same thing for the current through the inductor. What you find for time less than 0 by current continuity for an inductor has to be the same as the current at 0 plus. So we'll redraw that. And when we redraw this in that time region, because we're at DC steady state, nothing's changing, we replace all of our capacitors with opens and all of our voltage sources with shorts. We're going to have to define what our VCs are here. And we're going to have to define what our VLs are here. So for a passive element like an inductor, it always enters more positive and exits more negative. So that's our V sub L. And we could do the same thing for our I sub C if we wanted. Since we're defining it more positive in the top, we have to define our current going down. So armed with this, here's our VC that we want to find. Here's our resistor. Inductors during periods of DC steady state look like shorts. And we never have any switches or U of T's. We always evaluate them. So for time less than 0, this is 0, and we're left with just 2 amps. Okay, hopefully it's pretty clear by inspection that I sub L at 0 plus, there's only one source, and all the 2 amps will go through the short. And because there's a short here, our VC has to be equal to 0. Because the voltage across here is the same as the voltage across here, and it's connected by a wire. So there's our first step answer. Second step is to draw it at t equals 0 plus, and that's where we're going to find our initial conditions. And unlike step 1, where no matter what we're asked for, we always find V sub C's and I sub L's, here we're going to find what we're asked to find. So for problem A, we're asked to find I sub L. So we're going to find I sub L at 0 plus, and we're also going to find its derivative, I sub L prime at 0 plus. If I wanted to start off by finding I2, I'd find I2 at 0 plus and I2 prime at 0 plus. So we need to redraw our circuit again in this time of 0 plus. At time 0 plus, once again, there's no switches, there's no U of T's. All capacitors now look like voltage sources because of voltage continuity. So this capacitor looks like a voltage, and we figured it out. We figured it out right here. It's going to be a 0-volt source. That's the same thing as drawing a short. All inductors at 0 plus at that one fraction of a moment look like a current source. And we figured out what that is. Make sure you draw these things in the correct direction. We define isobel going down, so we have to define isobel going in the same direction here. And at 0 plus, this U of t turns on, so this becomes 4 amps. Now we draw on the things we're trying to find. So our isobel is this. We already found out what isobel is. It's trivial just looking at it. It's 2 amps. But how do we find the derivatives? We have to go back to the constitutive equations to begin with to find the mapping from non-derivative world into derivative world. And those 2 constitutive equations we said is IC is equal to C dV C dt, and similarly V sub L is equal to L I sub L prime. So this is the one we want to use because this is the one that's got this I sub L prime in it that we need to find. So we can solve that for I sub L prime, and that's 1 over L V sub L. So now we need to find out what our V sub L is in this time region. So I drew our I sub L, and according to the passive sign convention, voltage always exits more negative than it enters. So we have to draw our V sub L like this. So now the question is, what is that V sub L? The V sub L between this node right here, which is what we want to find, and this node, well, the voltage has to be the same everywhere along the node, right? So this is all this lower node. And what about that? It's all the same node. There's only one node in this entire circuit. It's the same node, so it has to be equal to 0. So this is 0 amps per second. And what that means physically is that at time equals 0, there's 2 amps flowing through that inductor, and at least initially, it's staying 2 amps. If we were to draw it in a graph, it would look something like this, and it'll either go down, or maybe it'll go up, or maybe it'll oscillate or do something, but it's going to start off with a flat slope. Now we can do the third step, which is to draw it at t equals infinity. When we draw it at time equals infinity, we'll find our I sub forced, and that's going to be a DC value. So at time equals infinity, it's DC steady state. We're not driving it with anything that's changing at time equals infinity. The capacitors, once again, always look like opens. The inductors always look like shorts. Now our current source at time equals infinity is going to look like a steady state 4 amps. And we want to find out what the current is through that inductor. That's going to be our forced current. So hopefully it's pretty clear just by inspection that this is going to be equal to 4 amps. It's all going to flow through that short, just like it did in the earlier example. Now the fourth step is when we find our alphas, our omega sub naughts, our s's, and if s is imaginary, or if s is complex conjugates, we'll also find our omega sub d, where the real part of s is our alpha and the imaginary part is our omega sub d. And then the last step is we're going to find the form of that natural solution of whatever we're asked to find. So the form has unknowns. Do not solve for your unknowns. So let's begin. There's 2 formulas to find alpha. One is if the circuit is in series, the other is if it's in parallel. This circuit is clearly in parallel, and so we'll use the 1 over 2 RC formula to find that out. That's going to be 1 over 2 times 10. Our capacitance, we said, is 100. So that gives us 1 over, let's see, 2/10, which is the same thing as 10 over 2, which is 5. The next is we'll find our omega sub naught. And that's always equal to 1 over the square root of LC. So for this particular problem, it's equal to 1 over 100 times 4. So that's going to be equal to the square root of 4 over 100, which is 1 over 25. That's equal to 1 over 1/5, which is also equal to 5. Since these two things are equal, since our alpha is equal to omega sub naught, we have the case of critically damped. And so now we can copy the critically damped equation right out of those student notes. It's equal to some unknown constant times e to the alpha t plus another unknown constant times t, e to the minus alpha t. And so that's going to be this. Complete with our unknowns. So this is the natural solution. Now we'll find the forced solution. It's always going to be equal to the current that we're interested at infinity, which we already figured out is equal to 4. So now we can find the total solution, which is equal to, this is our I sub L, our total solution, which is equal to our forced plus our natural. And now we can substitute in our initial conditions. So at t equals 0, plus this collapses down to C1. When we plug in 0 for t, this goes away entirely, and we're left with just plus 4. But we found our initial condition up here that it's equal to 2. So therefore, C1 must be equal to -2. Now we can take our derivative. So from up here, that's going to be equal to -5 C1 e to the minus 5t. We're going to have to use the product rule of differentiation to take the derivative of this. So we're going to take the derivative of t first, which is 1, and copy what's inside. And then we'll write down t without changing it and take the derivative of everything else. So that will be equal to minus t times 5 e to the minus 5t. And the derivative of 4 just goes to 0. And this derivative at 0 is equal to, plug in 0 for t, and we get minus 5 C1. But we already know what C1 is, it's equal to -2. And over here, when we plug in 0 for t, this goes away entirely, and we're just left with C2. We know from our initial conditions down here that the derivative has to be equal to 0 at 0. So therefore, we have 10 plus C2 equals 0, and C2 equals -10. And now we can solve the problem. I sub L for time greater than 0 is equal to C is equal to this, where C1 is -2, e to the minus 5t minus 10t e to the minus 5t plus 4. And all that's in units of amps, and all that's for time greater than 0. And actually, because this is the current through an inductor, and the current through an inductor cannot change instantaneously. If this is true for time equals 0 plus, it also has to be true for time equals 0. So we can even make it a little stronger by saying t greater than or equal to 0. Now, if the question was more complicated, if the question said find I sub L for all time, well, we already found what it was for time less than 0 up here. So if you wanted to, you could even add that it's also equal to just plain old 2 for time less than 0, and that's correct as well. Although the question just said find it for time greater than 0. Okay, so part B says find I sub 2 of t for time greater than 0. We could do the exact same approach to find I sub 2. Step 1 would stay the same. Step 2 would be different because now instead of finding I sub L and I sub L prime, we'd find I sub 2 and I sub 2 prime. But instead, there's a much smarter way to do it. Take a look at the original circuit and see if we can find a relationship between I sub 2 and I sub L, since we just did a lot of work finding I sub L. And for time greater than 0, looking at this, we can do a KCL up on top. And we can see that the current running out of this node has to be equal to the current that's going into it on the right. And for time greater than 0, it's always going to be 4 minus the current that has been leached through I sub L of t. Right? You can see that if we do the KCL right up here in yellow, that I sub 2 has to be equal to the current coming out of the node has to be equal to the current coming into the node minus this current that's coming out. Now we can simplify this a lot. We can say it's equal to 4 minus what we found out down here. That's minus 2 e to the minus 5t minus 10 t e to the minus 5t plus 4. So 4 minus 4 is 0. And now we're just left with 2 e to the minus 5t plus 10 t e to the minus 5t. And that's in amps. And that's our answer. And in the same vein of oversolving and finding more than we're asked to find, this is true for time greater than 0. If we wanted to, we could find what it is for time less than 0 too. Just by inspection, when we're looking at this time less than 0, all of this 2 amps goes through I sub L. None of it goes through that wire. And so therefore, since time for before time, none of it went through, we could add that as well. What happens right at time equals 0 plus, I don't know, and I don't care, because the amount of energy that it has between time equals 0 minus and time equals 0 plus is 0. So the amount that it could influence the world is 0. And if it can't influence the world, this doesn't mean anything to solve for it.